Alright, so here in lecture 14 we're going to take a look at what's called overloading functions. That is, having several functions with the same name that the compiler can distinguish from one another by their argument numbers and argument types. We're also going to introduce references, which are available in C++. They are a little bit like references in Python, and yet they are also quite different, so it can be rather confusing if you're comfortable with Python getting familiar with how references work in C++. And then at the tail end of this lecture we're going to look at something called the ternary operator in C++. It's an inline if-then-else kind of operator. So, first of all, overloading. You can have in C++ multiple functions that have the same name, and the compiler can tell them apart from each other if they differ either in the number of arguments or in the data types of those arguments. And this process is, as I said, called overloading. Now, we're already used to overloading. We just haven't really thought about it as anything special. For example, the plus operator, the binary plus operator, is used for addition. But if you add two ints together, that's a quite different thing from adding two doubles together. If you add one int to another int, what you're doing is you're adding a 32-bit representation of an integer to another 32-bit representation of an integer. That capability is built into the processor, and it results in a 32-bit sum of those two integers. On the other hand, 3.3 plus 7.2, well, conceptually, of course, that's also addition, but here, internally, the processor is adding a 64-bit representation of 3.3 to a 64-bit representation of 7.2, to come up with a 64-bit floating point representation of 10.5. So, same symbol, but internally within the processor, totally different actions are being performed. Here on slide 3, we have a couple of examples of overloaded functions, namely these two different versions of the add function. In main, we're calling add a couple of different places. In one instance, add is being called with two int arguments, and you'll notice if you look at these two different definitions of add that one takes int arguments and the other takes double arguments. So in this case, in main, the compiler will prefer to call the version of add that takes two int arguments because there's no converting that has to be done. Then later, if I add 2.2 and 1.1, the compiler will prefer to call the version of add that takes two double arguments. So if the compiler has a choice of several different functions that have the same name to call, the compiler chooses the function that has the best signature match with the call of the function. Now, the signature includes the name of the function and the number and data types of parameters. However, the return type is not included in the signature. So here on slide 3, the signature of the first add function is the name add and the fact that it takes two int parameters. The second one is also called add, and it takes two double parameters. So in selecting, the compiler notices that this first call of add has two int arguments, and therefore it chooses the add that has two int parameters. In the second case of the call of add, this call has two double arguments, and therefore it selects the one that has two double parameters. Now here, on the bottom of slide 4, we have two function definitions that have the same signature. They each have the name getVal and an empty list of parameters. So this is an error, and the compiler will flag this as an error when it gets to the second definition of getVal, whose signature looks identical to the previous one. So this process of deciding which of the various overloaded functions to call is referred to as overload resolution, and the details of this is ghastly. You can take a look at the full details of overload resolution in cppreference.com and various other sources. But for our purposes, we're going to be concerned with the three basic rules. First of all, if the compiler can find an exact match in which the name of the function and the function arguments have exactly the same number and types as a particular one of the overloaded possibilities, then that one will be preferred to all the other possibilities. If there is no exact match, but we can apply basic promotions, that is, small integer types to int, char or short or bool to int, as well as float to double, if there's one unique match involving promotion, then we'll prefer that one. If there's no exact match, and there's no unique match found using promotion, then the third step is going to be to try standard conversions. And this includes things like converting ints to doubles or doubles to ints to chars, chars to doubles, and so on. Now the problem here is that all of the standard conversions are considered to be equally valid, and so if the compiler cannot find one unique match involving standard conversions, then we still have a failure. So here are some examples on slide 7. Okay, actually let me put back up the code that we had on slide 3. So let's suppose that we have this call, add 5, 9. Now this is an exact match because we do have one definition of add that takes 2 ints, and these arguments are ints. So the compiler chooses the exact match in this case. In the case add of 3.3 and 1.0, again, the name of the function is add, each of the arguments is double, and we do have an exact match that expects 2 double parameters. This next case we can resolve by using a promotion. We can promote the character A to an int, and then we have found a match for this add function receiving 2 int parameters. On the other hand, in this last example where we have an int and a double, the compiler considers it equally valid to convert the 5 to a double precision 5.0, or to convert the double precision 3.3 to an int 3. And since there are 2 equally valid choices for the compiler to make here, you get an error if you try to compile this call of the add function, assuming that these are the only 2 possible definitions of add that are available. Okay, so the bottom line is that function overloading is allowed. An exact signature match is best. If there is no exact signature match between the call of the function and one specific definition of the function, then promotions are tried next, small integers to int, float to double. If that in turn does not produce a unique match, then standard conversions will be applied. Often when you get to this level of applying standard conversions, you'll encounter situations where there are multiple equally valid conversions, and it may be that no unique match can be found. Okay, so that takes care of overloading. All right, next we're going to take a look at references. And the key thing to understand about references in C++ is that a reference is an alternate name for some existing object. You cannot have a reference to nothing in C++. Any operation you do on a reference, such as assigning some value to the reference, is going to end up performing that operation on the underlying original object to which the reference refers. All right, so here on slide 9 we have a little bit of example code. I here has been declared as an int object, and I has been initialized with 4. The next declaration declares that Ri is a reference to an int. So notice that I'm going to read this from right to left as I have with pointers. This says that Ri is a reference to an int, and a reference has to be initialized because it has to refer to some existing object. In this case, the existing object that Ri is referring to is I. If I look at a diagram of what's happening here on the left-hand screen, we're looking at a diagram of what's going on in memory. Initially, I is allocated in memory as an int with an initial value of 4, and then Ri is set up as an alternate name for that same object. To differentiate between references and pointers, I'm using dots rather than an arrow symbol to associate or bind a particular name to a particular object in memory. So I, you can actually think of as being the first reference to this int object that's initialized with 4. Ri is then declared as a reference to an int referring to I, that is, referring to the same object as I. So I and Ri both refer to the same int object in memory. Now, the way that I've written reference is a common approach. This is the approach that Strostrup uses, and the ampersand is associated directly with the keyword int. However, remember that C++ is free format, so that doesn't actually matter. I could choose to write that Ri is a reference to an int by putting the ampersand directly next to the Ri rather than next to the int. And for that matter, I could have put spaces on either side of the ampersand. But the point here is that these notations are all the same. They say that Ri is a reference to an int, Ri is a reference to an int, Ri is a reference to an int. We must initialize Ri, and we have 3 different choices of initialization notations. We can use an equal sign, the old C-style way. We can use parentheses, the C++ constructor notation, or we can use curly braces, a more recent C++ notation. It's totally up to you which of these notations you decide to use. All that matters to the compiler is that the tokens have to be in the correct order. All right, here on slide 10, we have some example code that we're going to step through in these diagrams over here on the left-hand side. Our first statement here is I is an int initialized with 4. So I is bound to or associated with this int storage containing 4. Next up, we're saying that Ri is a reference to an int initialized to refer to I. So that means that Ri is also bound to that same int to which the name I is bound. And now we have that situation. If I display Ri, well, that's really equivalent to displaying I, and so the value 4 is going to be displayed on the screen. Now, if I display the address of Ri, a name does not have an address. A name is just a name. A name is just a label. It is the object to which the name is referring that has an address. And so the address of the object that the name Ri is bound to is going to be the same as the address that I is bound to. In other words, we're going to get the address of this 4 here, whatever that address is, and that will typically be displayed in hexadecimal on your screen. I'm not assigning the value of ampersand Ri to anything, so once I have displayed the address of Ri, that pointer value just sort of vanishes. Next up, I say Ri gets 7. Well, that means that the value 7 is assigned into the object that Ri refers to. The original value 4 in that object is now replaced with 7. Now, this is radically different from Python. In Python, if I said Ri gets 7, that would change the reference Ri to refer to the 7, leaving I as the reference to the 4. But in C++, once you create a reference referring to an object, you cannot change that reference to refer to some other object. The object to which a reference refers is fixed when that reference is declared and initialized. If I display I, well, I also refers to that same object, so I'm going to see the 7 that has been assigned into that integer object. Here I have a new integer object j, initialized with -3. All right. And if I say ri gets j, well, that simply means get the value that j refers to, which is -3, and assign that into the object that ri refers to. So that's going to end up changing the value of that blue int, which both I and ri are references to. Here I'm declaring another reference. I'm saying that r2 is a reference to an int initialized with ri. Now, a reference has to be initialized with the object that it refers to. In this case, ri refers to this object, so that's going to create another reference called r2 referring to that same object. So the blue integer here is now going to have 3 references to it. The initial name I and the additional references ri and r2. All right, so if I display the value of r2, the value that r2 refers to, that's going to come out as -3. Now, as a more useful and realistic example of references, let's take a look at a swap function that's using references rather than pointers to enable the swap function to change the values of variables that are actually back in the main function that's calling swap. Okay, so when we launch this program, the first thing that happens in main is that storage is allocated and initialized for the variables I and j in main. All right, so I is an int initialized with 7, j is an int initialized with -3, and now I'm swapping I and j. It appears that I'm passing values of I and j down to swap, but in fact, swap has been declared to receive a reference to its first argument and a reference to its second argument. The reference to the first argument will be called A, and the reference to the second argument will be called B. Each of these is a reference to an int. So when swap is called, this is what's actually going on. A is a direct reference to the same object as I. B is a direct reference to the same object as j. So when I start executing statements in swap, starting with int temp is initially A, well, temp is an int variable within the stack frame for swap, and it gets initialized with the value of A, but A is referring to this integer object containing 7. So temp now gets that value 7. When I say A gets B, that simply takes the value that B refers to, which is -3, and stores that into the object that A refers to. All right, so the -3, the value of B, gets assigned into the object that A refers to, which is main's variable I. In the final statement in swap, we say B gets temp, and that means that B, that is to say main's j, gets the value in the temp variable, which is 7. When I hit the closing curly brace at the end of the swap function, the references A and B, as well as the local temporary variable temp, disappear, and I find myself back in main with I now containing a -3 and j containing a 7. So I have effectively swapped the values of main's I and j variables by passing in references to those variables to this version of the swap function. Another use of references in C++ is for efficiency when you're passing large objects into functions. It's more efficient to pass a reference to const into the function rather than passing an entire copy of the object. Here on slide 14, we have the inefficient way of doing things. What we want to do here is to compare the hourly rates of two employee objects. We're using the parameters E1 and E2 for those objects. So when I call compare rates, an entire copy of the employee is coming in as E1, and an entire copy of another employee is coming into this function as E2. I'm then comparing the rates of these two employees, and I'm going to display the name of whichever of the two employees has the highest rate. Our employee objects are not terribly big. They have an integer ID, which is 4 bytes. They have a name, which is 10 bytes. They have an hourly rate, which is 8 bytes. But over time, our employee objects might become more sophisticated and larger, and so this could be an expensive amount of information to be passing down to the stack frame for this compare rates function. So here on slide 15, we're showing a call of compare rates. We have one employee J and another employee B. We're passing an entire copy of J as the first argument to compare rates, and an entire copy of B as the second argument to compare rates. But now let's look at a more efficient implementation of compare rates that actually will not cause us to change the implementation of main at all. So instead of passing copies of employees, on slide 16, we're passing as the two arguments, employee 1 and employee 2, a reference to an employee const rather than a copy. Now, call by reference is very efficient. It is as efficient as passing the address of the object rather than passing the entire copy of the object. And the const that we're putting in front here promises to whoever calls compare rates 2 that compare rates 2 will not change anything within these two employee objects. Our main function is actually not going to change at all, except for one trivial detail. Instead of calling compare rates, of course, we have to call compare rates 2, but other than that, the code looks exactly the same. So let's take a look at slide 17. Okay, looks exactly like the code on slide 15, except of course we're calling compare rates 2. I'm still able to pass J and B as the arguments down to compare rates 2, but what's actually being passed is, in each case, a reference to an employee constant. Okay, so that's an introduction to references and some examples of what references are used for. We'll see more uses of references when we start implementing classes. The final thing we're going to take a look at in this lecture is the conditional operator question colon. Now, let's imagine that you have some variable I that has been declared, and you want to set I to some different value depending on some test. So what we're going to do is we're going to say if some test expression is true, then let's set I to the value of some other expression. Otherwise, if the value of expression 1 is not true, let's set I to the value of some third expression. There's nothing wrong with that, but we can cut down the amount of code real estate we need to represent that by using our question colon operator instead of the if-else. The idea here is we'll evaluate expression 1. If expression 1 is true, then the value assigned to I will be the result of expression 2. Otherwise, the value assigned to I will be the result of expression 3. Now, we have a whole bunch of binary operators like addition and subtraction and multiplication and division. We also have some unary operators like unary plus and unary minus, likewise the ampersand for address of, or the star for contents at. Question colon is what's called a ternary operator because it requires 3 operands. The first operand is the test expression, and then the second and third operands are the values produced if expression 1 is true or if expression 1 is false, respectively. I do want to point out that if expression 1 is true, then expression 2 is evaluated and its value becomes the value of the entire expression. Expression 3 is never even looked at in that case. On the other hand, if expression 1 is false, then expression 2 is never even looked at. Expression 3 is evaluated, and its value becomes the value of the overall expression. Okay, so that gets us to the conclusion of Lecture 14, in which we have talked about function overloading, references, and the question colon ternary operator.